As promised, we'll do several examples in this video. I'm not teaching anything new. The problems are taken from the problem set that I'll have uploaded on the website, and I've written the numbers that these problems come from. All right, so how to solve this first matrix? We see that this is actually a permutation matrix. So we know that we have either a 1 or a -1, and the idea is to use the rules. So by attempting to restore the identity matrix, we are going to be able to find what the rule is. So the first, whether it's 1 or -1, it depends on how many row exchanges there are. So let me first try to restore the first row. So to do that, I see that the first row of the identity matrix is the second row in this matrix. So if I do this exchange, row 1 with row 2, I know that I will have changed the determinant by a sign. So I have to put minus, and then I can have 1, 0, 0, 0, 0, 1, 0, 1, 0. Now, by exchanging these two rows, I will restore the identity matrix completely. But the next row exchange, so note here I have equalities. Whenever we were doing elementary row operations on matrices, I always drew arrows. But here I have equality because these numbers are actually equal. So because I'm going to carry out another row exchange, which is now row 2 into row 3 and row 3 into row 2, what happens is that this minus now becomes a plus because I'm changing the sign one more time. And the matrix that I get is just the identity matrix, and I know that the determinant of the identity matrix is simply 1. So the determinant of this permutation matrix is also 1. Now, the second matrix is not a permutation matrix. What we can do here is we can do row exchanges, or we can do another trick. And actually, this is something to pay attention to oftentimes when you see determinants. So the sum of the terms in each column is equal to 2. If I add the 3 rows, I'm going to get 2, 2, 2. Now, whether it's 2, 2, 2 or 5, 5, 5 or 1, 1, 1, it's not important because I can factor a common factor out. So what I'll do is I'll add all those rows to the first. So I will do row 1 plus row 2 plus row 3, all in row 1. I know that this type of operation is not going to change the determinant. So I'm going to do this, and I know I just have equality, and I have 2, 2, 2, 1, 0, 1, 1, 1, 0. Okay, I have restored the first pivot. I can eliminate with that pivot. Now I can take that 2 and sort of factor it out if you like. So I know that I have 2 times 1, 1, 1, 1, 0, 1, 1, 1, 0. And now I can carry out elimination. I can eliminate with this first pivot, and I know that my determinant will not change. So the operations will be R2 minus R1 into R2 and R3 minus R1 into R3. The determinant will be 2 times 1, 1, 1, and then as I'm subtracting, I get 0, -1, 0, and then 0, 0, -1. Now I have an upper triangular matrix, and I know that the determinant of this upper triangular matrix is just the product along the diagonal, so my determinant is equal to 2 times 1 times -1 times -1, which is simply 2. You can try this for homework, and please do, by carrying out row exchanges, taking either the second or the third row in place of the first row and carrying out elimination. You should get 2 in any way. Now, what about the third row? So I can the third matrix. Immediately, this is just 0. Why is it 0? Because this matrix has equal rows. you can say all three are equal, you can say two are equal. Elimination will produce rows of 0, therefore that matrix would be non-invertible, so the determinant is simply 0. When you see a matrix like this on the exam, please feel free to just write 0. You don't have to eliminate to convince me that this matrix is non-invertible. Okay, now we have this matrix, and there are no real patterns here. It's just a 4x4 matrix. I better carry out elimination. So I will take the first pivot and eliminate underneath. The operations will be row 2 minus 2 row 1 into row 2 and row, I'm gonna have to bring all of this down a little bit. So row 3 plus row 1 into row 3. And I have not changed these operations do not change the determinant, so I just have equality. I have 1, 2, 3, 0. Then 0. 6 minus 4 is a 2. 6 minus 6 is 0. And then 1 minus 0 is just 1. Then I'm adding. I have 0, 2, 3, 3, and then 0, 2, 0, 7. Now I will eliminate with the second pivot. The operations are R3 minus R2 into R3, R4 minus R2 into R4. And I can do these operations because I know, you see, when we were writing the rules, it was always just one operation at a time. And you can do that. It's just that this operation does not change row 1, which is what I use to change row 3. So the fact that row 2 has changed has nothing to do with this operation. So one could carry these operations one at a time, and neither one changes the determinant, so we can also combine them. But it's very important that you actually use the rules in this way, that to row 2 you add a multiple of row 3 or row 1. If you are to multiply row 2 by 2 and write it as a new row 2, you will have changed the determinant. So this procedure where you start with the row that you are changing and you're not multiplying it by anything is very important. Otherwise, you will change the determinant. All right. So we have 1, 2, 3, 0 in the first row, 0, 2, 0, 1 in the second row. Then we have 0, 0, 3, and a 2, and then 0, 0, 0, and 7 minus 1 is a 6. And we are done. We have an upper triangular matrix. Now I know the rule for this. I just multiply the diagonal terms. 1 times 2 times 3 times 6. Feel free to compute what that is. I guess it's easy enough. It's 36. But if you leave it like that on the test, that is perfectly all right. I don't really care whether you can compute in your head or not. Of course, you also have calculators. All right. Now these matrices. Now the first matrix, if you just try to carry out standard elimination where you take that pivot and you try to eliminate underneath, you're going to get fractions and it's going to be ugly. You are not able to factor out 101 because it's not a common multiple. So factoring out to get a 1 here is not a good idea. Eliminating with it, also not a good idea. But let's look at the structure of the matrix. It's very interesting. So you have 101 plus 1 plus 2. 101 plus 100 plus 200. 102 plus 100 plus 200. So it feels like we can actually split out a bunch of hundreds in here. Also, we can use maybe linearity in the first row, or we can just try and bring out those differences, right? If you look at the difference between the second row and the first row, well, it's just 1, right? Everywhere. And if you look at the difference between the third row and the first row, the difference is a 2. And actually, that's the best way to go about it. So the operations that I'm going to carry out just by observation would be R2 minus R1 into R2 and R3 minus R1 into R3. So what I get here is 101, 201, 301. I haven't changed the first row, and now I'm subtracting. So I have 1, 1, 1, and then I have 2, 2, 2. Now immediately I know that this determinant is 0 because I could carry out elimination with this pivot. Well, not pivot, that's not a pivot number, but I could carry out elimination and get a row of zeros, or I can just use the fact that the third row is a multiple of the second row, so elimination would inevitably give me a row of zeros. I know that this determinant is 0. When you have one row being a multiple of another row, you just get 0. So a little bit of thinking, elimination here would not be the best way, but row operations that exhibit this structure are definitely useful. All right, and the last matrix. So here elimination seems simple enough because I have a 1 here, so I can just eliminate there. And let's do that. So I'll do row 2 minus t times row 1 into row 2, and row 3 minus t squared row 1 into row 3. And let's see what we get. So the first row stays the same. And in fact, the determinant stays unchanged because these are elementary row operations that I can carry out without changing the determinant. I think I'm going to need a bit more space here, so I'll just do that. Okay, in the second row, I have t minus t, so that's a 0 as expected. And then I have 1 minus t squared. And spoiler alert, you're going to have to compute with these letters, especially in the next chapter, so we might as well get started. All right, then we have t minus t cubed. Then we have t squared minus t squared, which is a 0. Great news. And then we have t minus t cubed. And we have 1 minus t to the 4. So that's quite a bit. Okay. Now, if we look a little bit in the second row, I see something. What do I see? Well, I see that 1 minus t squared is a common multiple. How do I see that? Well, t minus t cubed is t times 1 minus t squared. So I can factor that 1 minus t squared out. And what I have is here 1 minus t squared. It must be in parentheses, otherwise you have otherwise your expression would be wrong. So you have 1 t squared, 0, 1, which is perfect for a pivot. And then here you are left with a t, good enough. And then here you have 0. You could write this, if you like, as t times 1 minus t squared, which is probably not a bad idea. Oh, now when I say it, I realize I can factor something more out. Okay, so I'm going to slow down for a moment. T minus t cubed is equal to t times 1 minus t squared. So here I know that 1 minus t squared is present. It's a factor, right? What about here? Well, using some property, I'll write it and then I'll explain where it comes from. 1 minus t to the 4 is 1 minus t squared times 1 plus t squared. You can check it by just expanding and seeing that that's exactly it. But really where it comes from is the rule difference of squares. So x squared minus y squared is x minus y times x plus y. Again, to see that this is true, just expand here. What will happen is you'll have x times y and negative y times x, so those will cancel out and you will be left with x squared minus y squared. It is important, though, to be able to recognize that such an expression factors in that way, because you can't, when you see this, there is nothing to expand. You kind of have to know. So how does this apply to 1 minus t to the 4? Well, you can view 1 as 1 squared, obviously, and then t to the 4 is t squared squared. So your x is 1 and your y is t squared, which is why you can factor it in that way. So now I see that here I have 1 minus t squared, and here I have 1 minus t squared. So I can factor that out. So I will have 1 minus t squared coming from the second row, and another one of those coming from the third row. So really, to fix my work here, I just put a square there. So again, once from the second row, once from the third row. Then what I have in the third row is a t here and a 1 plus t squared there. So that makes the determinant nicer. Now I use this pivot to eliminate underneath. The operation will be R3 minus TR2 into R3. And what I get is, so I have to keep on copying 1 minus t squared squared times 1 t squared, 0, 1 t, 0, 0, and then I have 1 plus t squared minus t squared. So really just a 1. And what I see is the determinant of this matrix is just 1, because it's an upper triangular matrix with 1s along the diagonal. So ultimately the determinant of this whole matrix is 1 minus t squared squared. I know this may look hard, and for those of you who find these algebraic manipulations difficult or unnatural, the only way to become natural is if you practice. That's the only thing that you can do. Practice, practice, practice. Ask a lot of questions. If you don't know how to start on a problem, feel free to email me. I will be more than happy to point you to the right direction. And these types of examples or these types of problems, just like, this type, they will be a reoccurring theme until the end of the course. So you better start practicing and getting used to this. All right, that is all for today.